All right, welcome. This is going to be a course or play series on the design and analysis of algorithms, and this is going to be just a first introductory video where we're going to do a quick introduction to algorithm analysis. This image depicts Muhammad ibn Musa al-Khwarizmi, who was a Persian scholar who's best known for writing textbooks on arithmetic and algebra and importing the Indian number system into the West. His name Al-Khwarizmi was Latinized and then translated into a number of different languages in Europe, and in English his name got translated into the word algorithm, and so that's going to be the topic that we're going to be studying in this series of videos. All right, what is an algorithm? It solves problems, but not just any old problem, specifically an information processing problem, and that's what we're going to outline here. So it says here that an information processing problem relates an expected input to an appropriate output. So let's take a look at an example of what we mean by that. This is the minimum problem. So we've got it stated as an input and an output criteria here, where we can see that the input is expected to be a sequence of integers. So each one of these is an integer. This is using sequence notation or formalism that you can get from mathematics. And then the output here is just saying, okay, pick one of these, AI, such that AI is less than or equal to all of the other elements for all of the elements in our set. That allows there to be ties in case, all of them are 1, in which case there's still a minimum, it's 1. But this is just going to be a definition of how the input is related to the output. That's going to help us know if our algorithm is correct for this problem. It stipulates what is the correctness criteria for this problem. So then an algorithm is a strategy to solve the problem. In this case, we're going to use some kind of information processing operations to transform the input into the desired output. So how we do that, there's a lot of different computational methodologies that we might use. I'm using a very simple, iterative, looping structure. So we're going to start out with our input. So this is our input here. We start here by setting some m variable equal to the first element of our array. Then we iterate from 2 up to n. And in each step, we check if the new element is less than the one we've assigned to m. And if it is, we update m. At the end, we return m, which is going to be hopefully the minimum of our list. So now, how can we talk about specific problems that we might be facing? These are usually what we are facing in the real world. We're not facing some general problem of imagine you just have any old list and you're trying to find the minimum. That's the problem we were just talking about. But in the real world, you have a specific list like this one, maybe with 10, 5, 31, and 16, and you want to know the minimum of this list. And the distinction that we make between the general problem and the specific problem is what we're going to call the specific problem an instance. In this case, I say it's an instance is a problem with a specific well-formed input. In this case, we don't just say what the input should look like. We give you an example input that fits the criteria. So here's an instance to the minimum problem. One thing we can notice here is that there's going to be a relationship between the instance and the problem, the instance being specific and the problem being abstract. We can say that abstract or general versus concrete. Or this line here, this sort of faded line here, is separating what we might think of as the world of ideas from the physical world where real things happen. So in the real world, we might have a real list of integers that we really want to solve, we really want to find the minimum from. What we do is we idealize, meaning we turn that into a general problem, or we might say generalize, and we turn that into a problem. Then we can come up with an algorithm that solves the problem. Now, the algorithm is still abstract and it's still in the world of ideas. So it's not something that is physical that can live in the real world and solve problems for us. So we have to go back down again. That means we have to realize the algorithm somehow in the program. And what is that? Well, that means implementing the algorithm in code somehow. If you're a Java programmer or a Python programmer, you might implement it in your favorite language. Then you have a physical artifact. Okay, we don't usually think of programs as being physical because they live inside the computer. They're sort of electricity or something stored in some circuits, but they're still physical in the sense that they do exist in the real world and they can do things in the real world, meaning we can run the program on our instance and then that will solve the instance for us. So this is the relationship As computer scientists, we live up here a lot, taking algorithms to solve problems. But as computer programmers, we spend a lot of our time moving down this direction from an idea, a plan, an algorithm that we have in our mind into a program that's eventually going to solve our problem. Okay, so this circle of problem solving sort of goes on all the time in computer science, and you could be operating at any of these dimensions at any one point. And in this particular class, we're going to look at a lot of these transitions. We're going to spend a lot of our time up in the idea space, but we're going to talk about how that implements or how that impacts our implementation. Okay, so when we're looking at a problem and a potential algorithm for that problem, so we're up in the abstract, in the world of ideas, and we're trying to relate those two bits. Well, what makes it so that the algorithm, how can we say the algorithm solves the problem? Well, we say that only if it's correct, only if every time you give it an input that you would expect, a well-formed input, then you get the right output. So every time it finds the minimum element, not just some of the time. That's going to be our criteria for correctness, and our tools for proving something correct. There are a number of them, but very generally we could classify them all as proofs of correctness. We use a proof of some kind to prove that our algorithm does satisfy the output conditions for every possible input. Now that means we need to think about logic and how we're going to piece things together. But I've got a very simple argument here that says that this algorithm that we've designed for the minimum problem is actually correct. So let's start here with our theorem, where we see, first of all, I talk about the minimum algorithm. Well, what's that? That's this one over here. And it solves the minimum problem. What's that? That's up out here. Okay, so the minimum algorithm solves the minimum problem. That's what I'm trying to prove. I'm trying to prove the relationship between these two. Now, how am I going to prove this? Well, I'm going to talk about M. M is the sort of important variable that's doing some of the work inside our algorithm. Let's see how it starts out with my proof. I say the variable M keeps track of the minimum of the list so far. That so far is very important here. If you know a little bit about loop invariance, this is the loop invariant that we're talking about for this for loop. The minimum of the list so far. What does that mean? At first, when we initialize it to be a1, it's the minimum of just the first element of the list. Well, if the list only had one element in it, it's already its own that element is its own minimum. So when we initialize M to be A1, it's the minimum of the list so far just for the first one. So that's this first bit it says here. It is initialized to the first element, the minimum of the first element alone. And then at each step of the loop, okay, now we're in the loop. At each step, what do? We check, is there something else that's less than our current minimum? If it is, we update it. So it is updated if a new smaller element is found. Okay, at the end of the loop, so when we're done, so let's go step by step here. After one step of the loop, we now have the minimum of the first two. After two steps of the loop, we now have minimum of the first three. But after all the steps of the loop, we now have the minimum of all the elements. At the end of the loop, M stores the minimum of the entire sequence, and it is returned. Check, that's what we wanted. That's what we're supposed to return up here, something that is less than the entire sequence. Boom, we've proven that our algorithm is correct. Now, this is meant to be just a very quick example of a proof of correctness, not necessarily meant to be a model for something that you could use to build other proofs of correctness, other than you've got this general idea of how they work. This could be a model, for instance, to prove the maximum algorithm is correct. It might even be a good model for proving some other linear sort of simple iteration algorithms are correct as well. But in general, we'll look at some more proof techniques later on in this course about how to prove algorithms correct. So let's look at another dimension that we will be focusing on quite a bit in this course, maybe more so than correctness, is going to be the efficiency of the algorithm. And that's because correctness is usually assumed of an algorithm. If you don't have an incorrect algorithm, it's basically not very helpful for solving your problem, so you don't usually use it. But once you've confirmed that it is correct, then all of a sudden the really important things kicked in, which is, well, how much time does it take and how much memory does it take? And we're usually very opportunistic in the sense that we like to select the ones that are the fastest and use the least amount of memory. We want to use the ones that are optimal in some sense for our problem. So when we look at our minimum algorithm here, we might ask ourselves, how much memory does it take? I'm not going to spend too much time on that, but we might also ask ourselves, how many operations does it take? And to do this, we're going to use a sum here. And again, we've probably had some familiarity with summations. So here's our summation here. One thing I want you to notice is that it starts off at 2 and it goes up to n. Where did I get that from? Well, my for loop starts off at 2 and ends up at n. And this summation is meant to express the amount of operations carried out by this for loop. So it has the same starting and ending indexes, which is helpful for us. Won't always be the case when we're looking at a loop, but it is the case in this case. Then we might want to look inside the loop and say, well, how many operations are being carried out here? Well, we've kind of got this one comparison here. We might have an assignment here. There's some kind of branch going on here. I'm calling this a constant, and I'm going to give it the name D. And then also you'll notice there's this constant C out front here. Well, that's accommodating any other maybe operations that might be happening outside of the loop that are also going on. There's probably a constant number of them. I'm not going to nitpick what that constant is, so I gave it a name as well, C. And then finally here, we're going to just simplify this sum, and I'm going to do this very quickly here. The D actually comes out front here and gives us a D. What do we have replacing here? A 1. Now, when we complete that sum, actually looking at my slide here, I've got a little bit of error. So why don't we fix the error here? How many terms would they be in that sequence? Well, we started at 2. We didn't start at 1. My initial thought was there would be an n there, but it's actually going to be n minus 1. That does not change our conclusion, though. The function is theta of n. And that is going to conclude this video, however, which is a quick introduction to algorithm analysis. If you are interested or you're studying this topic, please follow on the following videos. Thanks a lot for watching.